Hello, welcome to the MADCOR laboratory at the University of Wisconsin-Madison. So MADCOR stands for Materials Degradation Under Corrosion and Radiation. I'm Professor Adrien Coué and I manage this laboratory at the university, and we focus on materials degradation in extreme environments. So the motivation behind creating this research group is relatively simple and stems from two different observations. One is a prediction from all energy agencies that by 2050, more than 50% of our energy production will come from fossil fuel. The other is a significant decarbonization effort that is needed to achieve a relatively manageable increase in temperature due to global warming. These two observations are highly incompatible, and working towards solving this problem is what gets me out of bed in the morning. Decarbonizing electricity production is only a part of the solution, but an important challenge towards global decarbonization. Looking at electricity consumption from France and Germany at the moment, it's quite clear that one of them is a good student while the other is not. And the main difference between the two countries, that's the reliance on nuclear energy source. So it's critical to support the deployment of current and advanced nuclear technologies if we want to reach our decarbonization efforts. One of the main limitations to the extension of current nuclear power plants and to the deployment of advanced nuclear technology is the development of materials that can sustain the high irradiation, high stress, high corrosion, and high temperature in these environments. Developing such materials and understanding their degradation mechanism to support a more sustainable future is really the vision of the MADCOR laboratory. To achieve this, we have a lot of laboratories and exciting tools available. We are located in the Engineering Research Building, where we have our high-temperature water corrosion laboratory, as well as molten salt and high-temperature gas corrosion laboratories. We also have the Ion Beam Lab in this building. We are at walking distance from the UW nuclear reactor, as well as the metal additive manufacturing labs. The Nanoscale Imaging and Analysis Center is right next door with all the microscopy tools. Finally, we have other laboratories for molten salt corrosion nearby and a lot of materials machining options, including the makerspace and the College of Engineering machine shop. For anything unavailable on campus, we work closely with national labs and industries. But to show you a little more what this is actually about, we will go over a few examples, starting with the corrosion and irradiation of nuclear fuel cladding that is used currently in light water reactors.
Welcome to the MADCOR Water Corrosion Lab. In MADCOR Water Corrosion Lab, we simulate the pressurized water reactor condition using the water circulation loop and the autoclave for the high pressure and temperature. One thing we are focusing on this lab is the Cherenkov effect. It's a kind of the optical sonic boom. The charged particles in the water, if that is travel faster than the speed of light in the water, it generates the blue light. And while the restoration of the medium and emitting the photons. You can see the photons right now. Prepare the glasses first. And whenever I turn on this UV source, you can see this kind of blue light. It is the phonon generating the blue light. So this kind of the phonon is irradiated on the surface of the pure cladding material or structural alloys in the nuclear power plant. And it modifies the corrosion mechanism of the materials. And for investigating that kind of the corrosion mechanism, we are using different tools like a Raman spectroscopy and the electrochemical impedance spectroscopy. Thank you.
We also focus on developing materials that are resistant to radiation damage. This is extremely difficult because neutron irradiation in nuclear reactors takes years and also produce radionuclides, which makes the materials very difficult to handle for characterization afterwards. So instead of using neutrons, we use ion irradiation that is much faster and also produces very little radionuclides in our laboratory.
To evaluate new materials for nuclear applications, we need to understand how particle irradiation can affect the properties of these materials. Typically, in our group, we're focused on cladding materials which contain the fuel in the nuclear reactor within the core, where you have the highest temperatures and the highest neutron fluxes, which means that these cladding materials have to be able to withstand the harshest environments within the reactor. If you want to test these materials in a nuclear reactor, such as a test reactor, this can often be very slow and very expensive, and often leave the materials activated and difficult to handle afterwards. Instead, here at the University of Wisconsin Ion Beam Lab, we use a particle accelerator to bombard our samples with ions, and using this particle accelerator, we can produce a lifetime's worth of reactor damage in just hours without introducing any activation or little activation into the materials. Currently, we can irradiate materials from room temperature up to 1000 C, and we can accommodate samples less than a square centimeter up to 100 square centimeters, which provides us the flexibility to perform a large range of irradiation experiments, including high throughput experiments, which can greatly accelerate the development of new nuclear materials.
Another area of research in the MADCOR group is the degradation of materials in molten salt reactors, which is one of the most promising advanced reactor designs. Salts can be quite corrosive for materials, and at the high operating temperatures, current code-certified materials are not able to sustain the corrosion induced by this harsh environment. So studying materials degradation in molten salt environment is of primary importance for the short-term deployment of molten salt reactor.
Hello, and welcome to our molten salt purification laboratory. So in order for us to actually test materials in molten salt, one of the first things we need is salt. And when it comes to how compatible a material is, one of the most important factors is how pure of a salt you're actually using. So to make sure that we're using the highest quality salt that we can, we actually purify our salts in this specially designed room which operates in negative pressure so that we can handle the dangerous gases that are required in a safely manner. So luckily nothing's on right now, so why don't we go take a look inside. When it comes to fluoride salt purification, two gases that you really need are hydrogen and hydrogen fluoride. We combine these two gases and we send them through a purification vessel where they bubble through the salt in its liquid state. Now, once we actually have purified salt, we have to transfer it out of that vessel, which sometimes can be very nerve-wracking and kind of fun to watch. So let's check that out.
To get the salt out of our vessels, we do this while the salt is in its liquid state, so at very high temperatures. In its liquid state, molten salt flows almost like water, and we can use pressure to push the salt out of the vessel while collecting it in compatible containers. The freezing process can also be fascinating to watch because you can see the salt crystals nucleate and grow. Now that we have high quality salt to work with, we can move to another lab where we will test materials in the salt to see how well they perform.
Welcome to the Molten Salt Corrosion Glove Box Lab. Regardless of whether or not our salts are purified, they are always going to be very sensitive to both oxygen and moisture. Behind us, we have our ultra-high purity argon atmosphere glove box. In this glove box, we have very low concentrations of both moisture and oxygen. This allows us to work with our salt and perform corrosion tests in this glove box. In this glove box, we have two furnace wells and corrosion cells that allow us to perform a variety of corrosion experiments on a variety of materials for molten salt reactors. These include both alloys and cladding systems. Cladding systems are composed of a substrate alloy with a protective corrosion barrier applied. These cladding systems allow for the rapid development of molten salt reactors since the cladding systems are not subject to the same ASME code certification standards. Now, let's take a closer look at one of the corrosion wells.
These corrosion cells give us the freedom to run many tests simultaneously and allow us to change virtually all aspects of the corrosion environment setup while making sample recovery simple.
With the proper safety equipment, of course.
Here we are recovering stainless steel coupons and salt samples from a recent experiment in a lithium, sodium, potassium fluoride salt known as FLINAC.
But the static corrosion testing cannot represent the real situation in molten salt reactor. So in this step, we are using a molten salt MADCOR loop to simulate the corrosion happening at the dynamic situation. Through employing radioactive isotope tracking technique by using the HPG detectors, we are trying to understand what's going on with the material corrosion and where is the corrosion products going in the molten salt reactor.
It is critical to characterize materials degradation in this extreme environment. So for this, we use in situ techniques that can give us information in real time. However, these techniques are difficult to implement, difficult to analyze as well. So we rely a lot on ex situ characterization, such as microscopy.
Here we have a scanning electron microscope where I will show you a demonstration on a sample of stainless steel alloy. I'm showing you a stainless steel sample corroded in molten salt, and this is a cross-section view. We can see the topology of the sample, and using the microscope I can focus the image so we can see clearly the features on the surface, and also we can use X-ray detector where the X-ray will be emitted from the sample in order to have the chemical composition of the alloy. So in order to study the samples in a smaller and finer details, we need to use transmission electron microscope. So this microscope uses an electron source where electrons are emitted and focused through electromagnetic lenses. And will be interacted, the electrons will interact with the specimen that is in the sample holder. The sample holder will go inside this hole, and then the electrons will be diffracted from the sample and then go into the objective lens and projector lens, and then we have it on a fluorescence screen. This is an example of low magnification electron micrograph image of high entropy alloy being irradiated at 200 display per atom at 500 degrees Celsius by 5 mega electron volt nickel ions, and we can see clearly the void swelling in the sample due to irradiation.
Modeling materials degradation is also critical to predict materials behavior in given operating conditions. At MADCOR, we develop corrosion models that are multi-scale, from first principle physics to finite element modeling, and we use our experimental data to validate them. So in conclusion, at the MADCOR laboratory, we try hard to develop better materials to support a faster and stronger nuclear energy deployment towards a more sustainable future. I hope that you'll come and join us to be part of it.